This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
For Software Engineering Radio, this is Robert Blumen. I have with me today Iljitsch van Beijnum. Iljitsch is a freelance network specialist and writer in the Netherlands and is active within the Internet Engineering Task Force. He is the author of the book BGP, Building Reliable Networks with the Border Gateway Protocol, and is the author of a forthcoming ebook on Internet routing with BGP. Iljitsch, welcome to Software Engineering Radio.
Thanks for having me.
Today, we're going to be talking about internet routing and BGP. Before we can even have a conversation about BGP, we need to cover some basics on what the internet is and how internet routing works. I've came across this explanation of the internet as a network of networks. Can you explain what that means?
Well, at home, you probably have your own network. Could be a very small network with just a home Wi-Fi router and then your phone and your laptop and so on connecting to it. Organizations also have their own networks, much larger networks. But the thing is, all these networks are connected together. Together, they make up the internet.
What is the atomic unit?
Well, I guess anything that has its own IP address. So that could be a very small device, probably not as small as a smart light bulb, but and anything up from there is the most basic internet connected thing you can get.
We have groupings of internet addresses into what's called an autonomous system. Can you explain that?
Well, the thing is, as we get to talk about BGP, some organizations have a network that runs BGP, and then you have to somehow demarcate that network. So that is what an AS is, an autonomous system. And they all have their own number to keep them apart.
Where does an autonomous system get its number from?
Well, there are 5 regional internet registries. They give out IPv4 and IPv6 addresses and AS numbers.
And these autonomous systems, what kind of real-world entities do they correspond to? Is that a corporation, an ISP, or what?
Well, certainly all the ISPs, because you need an AS number to run BGP, and you need BGP if you connect to more than one other network. So at home, you just connect to one ISP, so you don't have to have your own routing policy where you say some packets go to the left, some go to the right. They just all go to the ISP, so you don't need any complex protocols for that. But the ISPs, they connect to multiple other ISPs and other networks, so they need to run BGP. They are an AS. Also, content networks. Sometimes organizations or enterprises such as banks, they often are ASs, but lots of them, even fairly big networks, they just connect to one ISP, so they don't need to be their own AS.
Is there any data on how many, and by AS you mean autonomous system, how many ASs there are on the entire internet?
I could check, but I think the last time I did was 70,000, something in that order.
If you're a business and you need to get on the internet, you might start out by getting an ISP and connecting you. Is there some point where you get big enough where you say, we're going to become an AS?
Well, the big thing is connecting to more than one ISP. So that's usually for redundancy because you can't afford any long outages, but it can also be to save money. So for instance, if you connect to other networks directly, it's cheaper than to pay an ISP to do it for you if you have a large network. It used to be that even somewhat smaller networks, they would save money by connecting directly. But these days, you have to be really huge because the ISP prices have gotten a lot lower.
So talking about ISPs, are there different types or tiers of ISPs?
Yeah. So the main thing is that what we call the tier ones, those are so big, they can't find anyone even bigger to buy service from. So they have to handle all their stuff on their own, and they have to connect to all the other tier ones. It's about 12 to 15 of those, and all the other ones are lower tiers. We don't really count If it's 2 or 3 or whatever, usually it's the big ones and the smaller ones.
Okay. If I have home internet, then I'm going to be contracting with a smaller ISP, and they're going to upload, or not upload, but some of their traffic will be routed up to a tier 1. Is that how it works?
Yeah, so also difference that we usually recognize is between ISPs that provide connectivity to home users, small businesses, and then the ones that carry traffic really long distances across the world. We usually call them carriers. So usually you have for instance, Comcast is huge ISP, but they are not a carrier. They don't connect to all the different regions in the world. So they connect to one or more carriers. Also, they connect to other networks directly, so they don't have to go through the carrier to save money.
Now, are carriers also the same as tier 1, or
all
different?
The tier 1s are carriers, but there's also carriers who aren't tier 1.
Okay. And you mentioned Comcast, which is certainly a popular ISP where I live. What are some of the names of some of the tier 1s? And are those known to the public, or are they insider names that you'd only know if you're a network engineer?
Yeah, the thing is they keep merging. So the names keep changing. But I think AT&T is still one. Then we have Tata. It's a big Indian enterprise that has all kinds of different businesses, and including being a carrier. Verizon Business, although they changed the name of their network a bunch of times. Yeah, and probably names like Tele1 or Deutsche Telekom, but I don't think they are very active in the US. Or are they a tier 1? I think so, I'm not sure.
The next one of our building block topics will be IP addressing. Start with, how does an entity on the internet obtain an IP address?
So the big difference between an IP address and an Ethernet address is that the Ethernet address is burned into the Ethernet chip or the Ethernet card in the factory. So you just get it and it's already there. So you don't have to do anything for that. But with IP addresses, that won't work because there are so many addresses, and all the routers need to be able to find a path to each individual IP address. So there would have to be billions of entries in the routing table. So to avoid that, what we do is we hand out blocks of IP addresses. And then, for instance, in a university, you have maybe a few thousand IP addresses, or you used to have that before they became scarce. But you only have one entry in the routing table. And then inside the university network, they know where all the IP addresses go. So you usually get those from your ISP. But if you're an ISP yourself, or if you want to run BGP, you get it from the regional internet registry.
The university, it wants one or a few IP addresses. Who does it request them from, and how are these requests handled? Okay,
now suppose the university doesn't run BGP themselves. So the easiest thing to do is just ask their ISP. Usually that's basically part of the setup process if you become a customer. And usually you need at least 256 that's the smallest block that is handled in BGP. So for instance, if the university then says, well, I want to connect to other networks as well, or two ISPs, then they have to adopt BGP, and they probably have to get a new block of IP addresses at that point. And then if it's an American ISP, an American university, the North America is served by ARIN, the American Registry for Internet Numbers. So they'd have to become a member of ARIN and request 256 addresses from ARIN, IPv4 addresses.
As a home user, I get an IP address from my ISP. Did my ISP go through that same process to get a block of IP addresses, which it then hands out to its customers?
Yes.
And that might be a much larger block because ISP has tons of home users.
Right. So those are tens of thousands, hundreds of thousands, or even millions.
Okay. Can you provide the history of the concept of class full and classless IP addresses?
So the thing is, I already told about how ISP would know only the range of addresses that is used in the university network. So there's bits in the IP address that are the same for all the IP addresses inside the university. And then there's, so that we call that the network part. And then the remaining bits are used to number the individual systems in the university. So that is the host part. And it used to be that there are 3 different classes of IP addresses. One where the class A, where the network part is very short. So you only have a few networks. But then the host part is very long. So you can have many hosts in a network. And then class C, where it's the other way around. Very many class C networks. And then only 256 hosts per class C network. And then class B splits the differences in the middle. But at some point, for instance, these universities again, suppose in the 90s, you needed to hand out 4,000 IP addresses to 4,000 PCs in the university. Well, class C is too small. 256 doesn't cut it. Class A is 60 million addresses, way too much. So you get class B, 65,000 addresses. But there's only 16,000 class B blocks. So you waste 60,000 addresses, use only 4,000. That didn't work. So then what they said is, we'll just switch to class C and have, for instance, 16 class C blocks for one university. But then the routing table started growing really, really fast. So basically the routers exploded. So then they said, well, let's get rid of this artificial limitation of these 3 classes and just say we cut wherever we want. And that is classes into domain routing.
Okay, so if I understood that there are the 32 bits in the IP address, and then there's been a lot of changes over time in how many of those bits are the organization part that are consistent across one organization, and then how many are the left for individual nodes on the network?
No. It used to be that there were just 3 sizes, but now the size is whatever you want.
Whatever. Okay.
So if you need, for instance, 400 addresses, you get what we call a /23. So 23 bits are for the organization, 9 bits left, 512 addresses. So you only waste 100.
I should ask briefly about IP4 versus IP6, although that won't be the main focus of our discussion. But how did things change with IP6?
Well, in this regard, they didn't really change, except that there's now 128 bits.
Okay.
So a lot more bits.
Okay. Now, I want to move on and talk about routing. I'm using some device. I need to talk to another server out there, whether I'm sending an email, internet. How does the packet get from one IP address to another IP address? And how many different kinds of things does it have to cross on the way from A to B?
Well, what happens is that the software inside your computer creates IP packets. So, for instance, we send an email and the mail is a bit longer, has to be split in a bunch of IP packets. Those all get an IP header with some information in it. The most important part of that information in the header is the destination address. There's also the source address, so the return packets can come back. But the destination address guides the packet along the way. So then your computer probably doesn't have a big routing table inside it. So what it does, it sends the packet to the default router. That's what you get through DHCP. So as soon as you connect to a network, DHCP tells you what the default router is. Send the packets there. And that router, if it's, for instance, a small home router, it also has a default router. That's the other side of the line to the ISP. And then it gets to, for instance, the first ISP router. And then there's actually a decision to make. So do I go to the north, to the south? Which exit do I take out of the network? So these routers get bigger and bigger, and they have more and more choices of where to send stuff. And then eventually it gets to the right ISP. Maybe there's a carrier in the middle, maybe even 2. It gets to the destination ISP, and then it goes to the right router that the other side connects to, goes over the line to the home router, and that one finds the Ethernet address that goes with the IP address and delivers it over the Ethernet. Or Wi-Fi, works the same.
So at each step, each router is looking at its routing table, deciding where to send the packet next.
Yes.
And a routing table, it's some kind of a data structure. What is it exactly?
Do you want some details?
Yeah, we're all about details on this podcast. So.
Okay, so the thing is, there's actually 3 tables. So there's a BGP table that stores all this BGP information. Then there's the main routing table that collects all the information from all the routing protocols that run. There's usually an internal routing protocol within the AS. So there's 2 routing protocols. And then it goes to the forwarding information base. And that's the table that's actually used to forward the packet. So that one usually gets millions of packets per second, or at least it's built to handle millions of packets per second. So you need to be able to go through that data structure really fast. So there's basically 2 ways to do that. You use an ASIC that can search through a data structure in RAM really fast, or you use content addressable memory, TCAM, ternary content addressable memory. So you can have wildcard bits in your search question. And that's basically memory with tiny bit of processing power in it. So every memory cell can do a compare and see, is this the prefix, the address block that this address falls within? And it says, yeah, that's me. So you don't need to go through all the sequentially through a bunch of memory locations. The memory can do it itself. If it's in software or if it's in RAM, then usually we use a tree. So not a binary tree, but a tree with, for instance, that splits in 256 different leaves, or radix tree.
Okay. Now, it wouldn't be feasible to have an entry for every single IP address. What I understood from your discussion is it relies on destination address falling within a range of IP addresses by some of the higher order bits matching, and that is considered a route match. Is that correct?
Yeah, that's a prefix match. So basically, like I mentioned before, if you have a block of 512 addresses, so then the organization part, the network part is 23 bits. So we write it down with a slash and a 23 at the end. So a slash 23. And that means that in the data structure, basically the remaining 9 bits, they are left 0. But then you can have a mask. So you to mask out the bits you don't want to match, or you can use some other mechanism. And the thing is, because these prefixes can overlap, so I can have the 23, but also within the slash 23, there's 2 slash 24s. So if these are also in the routing table, I match the slash 23, but I'll also match one of the slash 24s. And then the rule is longest match first. So the match with the lowest number after the slash, the shortest prefix, that one wins.
Okay, I'm glad you said that, because I was going to ask if there could be more than one match. That sounds to me like saying if I know you live in a certain neighborhood, that's more specific than if I knew you lived in a certain city or region. And so if we route it to the neighborhood, we're getting closer to you than if we just said route it to Netherlands.
Right. So I misspoke just now. I said the smallest number after the slash, but it's actually the largest number after the slash. So the longest match.
Yes.
So the example that I often use is, for instance, if you are driving from the East Coast to California, or actually you're driving to San Francisco, and there's 2 signs, the road splits, and one sign says California to the left, and the other says San Francisco to the right. So you need to go to San Francisco, it's in California, so you go to the left, right?
Got it.
So no, that doesn't make any sense. Because why would there be a separate sign pointing in a different direction for something smaller? That doesn't make any sense to use the larger, less specific information. So actually we apply this algorithm ourselves as well without realizing it.
And how big in terms of either the number of entries or maybe the number of megabytes or gigabytes are routing tables these days?
There's in BGP a bit under 900,000 IPv4 prefixes and about 125,000 IPv6 prefixes.
So one thing I've wondered about is certain small countries have created a profit center by licensing their domain, their
Right.
top level domain, because it happens to match an English word like .me, I think it might be Montenegro. If these routing tables have a premise of a bunch of things are close together because they're all in Montenegro, and we are going to be able to route traffic to those domains to Montenegro, and those entities are assigned certain IP addresses. But now I'm in California and I got a .me because it's cute and funny. Does that create issues with the routing not working the way it was conceived? Because you have people all over the world who are now on this same top-level domain?
Well, the domain names and the IP addresses are completely decoupled because the DNS sits in the middle, so it maps one to the other. So you can easily map one name to addresses that are used in Holland, and the next name, one letter up, to something used in South Africa, completely different addresses. So
there's no reason to assume that a bunch of domains issued from the same place are going to have to need IP addresses that are also issued from the same ISPs.
No.
Okay, so that was my flaw. Great. Now, within the routing table, could there be multiple alternative routes to the same range, or has something else, the thing which built the routing table, already decided what is the best route if there were multiple routes?
Well, obviously, the whole idea being that you need to make a decision where to send your traffic. So you always have, or usually have, multiple options. And then BGP decides which option, which path is the best one. And it gives that one to the master routing table inside the router. And then maybe there's another protocol as well that also says, I can reach this. And then the two protocols have to duke it out in the master routing table. But as far as BGP is concerned, BGP knows what's best in BGP, except when they're completely equal and you want to actually load balance across multiple paths. But then there are some special conditions that have to be met.
Okay, so we may come back to that. In my home computer, then I'll have a simple routing table, which is saying anything that's not on my local network, send it up to my ISP. And then I would think my ISP would have relatively simple routing table because it's connecting to, everything is going to go to one of a number of carriers or tier one. So it only has to group things into 8 or 10 buckets to know which carrier.
Yeah, but the thing is, it's like from the standpoint of that first router that doesn't have very many options, it's like there's only 10 phone numbers in the phone book. So actually, you, for instance, could just shrink them down to one digit. But it's still the entire phone book. It's just that the numbers are very short.
So it's okay. The number of values is small, but the number of prefixes is still the same. Okay. And so how are these routing tables? I'm wanting to build up where I can then ask you what is BGP. And the next question I have is, how are the routing tables constructed? Now, if we have to talk about BGP first, then go ahead and answer that question however it makes the most sense.
Well, like I said, router will probably be running 2 or maybe even a few more routing protocols. So each routing protocol just says, I can reach this prefix, and attaches usually some value, a metric to it of how well it thinks it can reach it. And then this master routing table is built from that. And that one is then used to create the forwarding information base. So that's basically just manipulating data structures in software.
Okay. So is there a program running on each router that is taking in information about routes and updating the routing table?
Right. So for instance, there's open source software that implements a bunch of routing protocols on the Unix-like systems. It's called Zebra. And it has a daemon for every protocol, and then one master daemon that gets all the information for all the other daemons and collects it into the master routing table. And then it goes inside the kernel of the Unix system.
And it then, when it sees changes that would impact the routing table, it applies an update to the routing table?
Right. Yeah.
Okay. And how rapidly are routing tables changing over the course of a day?
Well, OSPF is a widely used one inside an AS, and that one detects other routers if they go away, if they appear within about 10 seconds. or a small multiple of 10 seconds. And then if an existing router that's already connected to the other ones has an update, it can happen in a second. In BGP, it's because it's the entire internet. It takes a bit longer, especially for an update to be flooded all across the internet. But that could be within a few dozen seconds or maybe 1 or 2 minutes.
Okay.
To reach the entire internet, right?
Okay. So you mentioned OSPF. I'd like to drill down a bit into that. So first, do you know what it stands for?
Open shortest path first.
Okay.
And shortest path first is the SPF or Dijkstra algorithm by my fellow countryman who worked in Texas for a long time. And that's an algorithm to find the shortest path between two places in the network.
Okay. So what are the inputs to this algorithm and what does it produce?
Basically, it's a graph. So I have a bunch of nodes and this one is connected to this one and so on. And then it runs through that until it's determined the cost to reach every other node from the start, from where you are.
Okay. And so to back up to earlier response you gave, you said there would be a daemon running OSPF on each router, and it's getting updates that it can use to recompute what the graph looks like. Is that correct?
Right.
Okay.
Yeah. So in OSPF, there's actually, they call it OSPF database. So that's basically the graph of the network, which cost value attached to every nodes that are connected. And then when there's an update, it updates its own data, sends out the update to its other neighbors. And then it applies the update itself on its own database, runs the SPF algorithm again, and then sees that it needs to take a different path to reach certain destinations because now something has changed.
OSPF, if I understood this, it maintains its own model of what it thinks the entire internet looks like.
No, OSPF doesn't work internet-wide. It's what we call an IGP, internal gateway protocol, an internal routing protocol. So it runs within a network operated by one organization, within one AS.
Okay, what is the extent of the graph that OSPF models?
It's the connections between all the routers. So if you have, for instance, 20 routers, and on average they are connected to 3 others, that is 60 links that you have to put in the database. And then the list of prefixes that each router sends out into the network.
So things that would change the graph would be new router is added, a router goes away, or an existing router is aware of a change in its ability to access parts of the internet. Are there any other types of events that would cause a rerun of OSPF?
Well, from the simple brain cells of this daemon running inside a router, it's very hard to make the difference between a router going away and the link to a neighboring router going away. So I'm not sure if that is something that is different in OSPF. But one disclaimer I have to make, that is BGP, that I wrote this book on. It's relatively simple. It's the BGP standard is, I think, the old one about 50 pages, but OSPF is 150 pages, much more complex. So I'm not an expert in OSPF. So basically, you see a router on an interface, on a network interface that wasn't there before. Could be because the router just turned on, could be because the link came on, and the opposite. The router goes away, doesn't answer anymore to the keep alive packets, the hello packets. It could be because the router went away, could be that the connection went away. So those are basically the two events. And then there's, of course, what also can happen is that a prefix goes away. So the router is still there, but now says, don't send me traffic for this prefix anymore, or a new prefix is advertised.
If I had in my routing table, I'm the router, that router was formerly the best route to that prefix. Now the router says that prefix has gone away. Don't send me any more traffic to that. That would force SPF to revise its notion of where is the best route to that prefix and possibly change the routing table.
It would change the routing table, but it wouldn't have any impact on SPF. SPF is just a graph between the connectivity between the routers. So then there's a second part of the database that maps the prefixes to the routers.
Elastic enables the world's leading organizations to put their data to work using the power of search. Whether it's connecting people and teams with content that matters, keeping applications and infrastructure online, or protecting entire digital ecosystems, Elastic's search platform is able to surface relevant results with speed and at scale. Learn how you can get started with Elastic's search platform for free at elastic.co/SERadio.
So I think with these building blocks, we are ready to take on BGP. I want to start with, what does it stand for?
Well, BGP is the Border Gateway Protocol. And now you may ask yourself, what is a border gateway? But back in 1989, when BGP 1 was created, then they often used the word gateway for what we call a router. So basically, it's border router protocol. And a border router, well, that makes sense. That's the last router in your network that talks to the first router in the next network. So it's the protocol that the border routers in different networks talk to each other.
If you had to come up with a better name for it that's more in line with modern usage, do you have an idea for that?
Well, I think border router protocol would make more sense. Protocol used before we had BGP was EGP, and that was the exterior gateway protocol. So but I don't think people would understand that. Also, that name is already taken in the past. So something like interdomain routing protocol, but that one is also used for something that nobody remembers anymore. So it's hard to find good names.
Okay. And what is BGP?
Well, like I said, it's a routing protocol that your routers use to talk to routers operated by other people.
Okay.
That is BGP.
Could you give us a brief history of BGP?
Well, the first version was in 89. And then within a few years, they went to version 2 and 3. And then version 3, that one was used when this whole thing where the routing tables started to explode because they went from Class B networks to multiple Class C networks. So they had to figure something out. So that was classless interdomain routing. And BGP4 is the BGP version that supports classless interdomain routing. And we still use BGP4. So that was in 1993, and it's now 2021. So that was a very successful protocol version.
Pretty stable.
Yeah. Well, but that doesn't mean that nothing has changed. For instance, right around the same time they created BGP4, they were working on IPv6. So BGP4 predates IPv6, but still we can use BGP4 to route IPv6. And that's because there's extensions that are added to BGP4, but they didn't have to go to a new version number.
Something I wanted to ask before, I think it makes sense now, is in terms of megabytes or gigabytes, how big are these routing tables?
That's hard to say. So the first time I ran BGP was in 1996 on a Cisco 2500 router. That one has 25 megahertz 86030 CPU and 16 megabytes of memory. And that just about fit. So that was 5 megabytes for BGP, and there was 30,000 prefixes and 5 megabytes for the main routing table. So we are now at about 30 times that. So that would be about 150 megabytes for each table, but that assumes that the data structures are the same. And because memory is cheap now, it's probably a bit bigger than that, but order of a few hundred megabytes for one BGP feed. So if you connect to multiple other networks, multiple routers, they all send a copy of their BGP table, so that can add up. So it's one copy of the BGP table for every BGP router that you talk to, and then one extra for the main routing table, and a last one for the forwarding information base.
Okay, I can't do the math in my head, but to what extent were changes in how the internet works driven by realistic amount of memory that you could put in a router?
I don't think that was the big limitation. I mean, it's always possible to add more memory. I mean, it might be expensive, but there's not really a limitation on how much memory you can put in a CPU or attached to a CPU, except for, of course, when you had to jump from 32-bit to 64-bit. But I don't think that was an issue. That happened for other reasons than purely memory size in routers. I mean, even today, probably don't need more than 4 gigs in any router except maybe the largest ones.
Within the BGP protocol, what are the most important messages that are exchanged between routers?
Well, there's only 5 messages. And the main ones are, there's the open message that starts the whole thing. Then there's the update message that sends the other router one or more prefixes with some extra information attached, or says withdraws prefixes that were sent in earlier updates. And then when there's no updates to send, then there's keep alive messages to make sure that the other side doesn't think we went away.
How does the BGP interconnect network bootstrap itself when routers come on board?
Well, interesting thing about BGP is that unlike all other routing protocols, it doesn't automatically discover other routers. So it needs to be configured on 2 routers to talk to each other. So when they boot up, when they power on, and then their network interface comes up, they start connecting to the IP address of the other router over TCP. When there's a TCP connection, they send the open message and they start exchanging information. And each router has one or more prefixes of the IP addresses used in the AS itself. So then they exchange those. And then maybe one of the routers connects to a third network. And then maybe it gets prefixes from that network and sends it in an update to the first one. And so the more stuff connects, the more updates flow in all directions. And those 900K prefixes are put in the table. If you turn off the entire internet and turn it back on at the same time, of course.
If you are going to add a new router, you're an ISP, then you need to configure your other routers to say, for BGP purposes, here's a new router that you need to connect to that you did not know about before.
Yeah, that's a really annoying limitation because the job of the BGP routers is to talk to other networks, but they also have to coordinate their information with each other. So they also need to talk to the other BGP routers in your own network. And then originally the basic rule is that every BGP router in an AS must talk directly to every other one. That way you can't have loops in the information because it can only come from the source. Now, if you have 100 routers, you put in number 101, that means you have to log in to 100 routers and add a BGP neighbor to the new one. Yeah, hopefully, if you have 100 routers, you have some automated system for that. But of course, that is quite unworkable. So there are solutions to get around the limitation.
This, I think, illustrates a general principle you see in a lot of things where we have all these great protocols like DNS and BGP that help our applications discover things. But at some point, something can't be discovered. It has to know where stuff is.
Right.
Okay. Now, suppose I'm an ISP and I'm going to add a new router that I want to interconnect with a tier 1 or other ISPs. Do I have to tell them, guys, I'm adding this new router. Here's the IP address. Whichever one of your routers you want to connect to me, it has to now know about this new IP address?
Yeah, so if you have an existing router and you replace it, then you just put all the information from the old one into the new one, and then basically the other side doesn't really have to know anything. Well, you probably want to tell them I'm going to do maintenance, so we'll be down for an hour or something, but there's no change for them. But usually the way it works is that if you want to connect a new router, of course, it has to connect over some network connection. So usually you order a connection from an ISP, and then you talk about the BGP information, the settings on the two sides that you're going to use.
Okay. And what happens if a router cannot connect to an IP address where it believes there should be another router?
Just keeps trying.
Keeps trying. Okay. Now, so let's drill down a bit more into the update message. Could you explain with an update, what are the fields and the data in the update?
So basically, it's all binary, right? So this is all the 90s, so no XML or anything. And there are 3 parts. The 2 parts have a length. And then because the message itself also has the length, that means the last part, the length is implied. So the first part is NLRI. That is network layer reachability information. And that is a really fancy way of saying one or more prefixes. So that's just the IP address prefixes. And then we get the path attributes. So that's additional information attached to these prefixes. And then the last field, and all these path attributes, they all have their own structure because they're all different. Some are optional and some are required. But then the last part is the withdrawn routes. So that's prefixes that are no longer reachable.
Okay.
So that's what an update looks like.
So update is a router saying, here's some prefixes which I am able to route to. Or here's some prefixes which I am no longer able to route to.
Yes.
Okay. You're a router, you're getting BGP updates, and updates tell you that certain routes that you were not aware of before now exist, or routes which you had have gone away. And then that drives the routing algorithm, which will then eventually may apply updates to the routing table if either you have a new route that's better or a route that was the best route is no longer available. Was any of that correct?
Yeah, that's right. And then there's a third thing that can happen, that is that you have a prefix that was already there, but now the path attributes have changed because there was some update somewhere else. For instance, the path got longer, so it's still reachable, but now maybe because it's longer, you want to use another one.
Okay, so previously it took me 5 hops to get to a certain address range, but the topology of the network between me and that address has changed, and now it takes 7 hops. So you want the other routers to know that, because now that may no longer be the shortest route if it's gone from 5 to 7.
Right. It could be that it might still use a longer one because the length of the path is not the most important thing, but it is important. So it could easily be that it now selects another one.
Yeah. Okay. So that gets into what by shortest or best route, what kind of a metric are we using to decide on the best route?
Well, I'm glad you asked because there's 13 simple rules. It's actually a fairly involved algorithm to decide. And the thing is that you need to resolve this. You can't say, okay, I don't know. I can't make a choice. You have to make a choice. In the BGP specification, it goes to G. How many is that? That is 7 plus another one. So that's 8. And like I said, the 13, that's on Cisco's website. Cisco has a few extra they invented themselves. And most other routers, they use the same logic as Cisco. So do you want me to discuss the main ones?
I'd like to save the time, or we have a bit of time left. And I wanted to save the time to go into another topic, which is the discussion of what can go wrong with BGP. As I understand, it's based on a trust system where if I'm a router and I say, hey, I have some great routes to these prefixes, then other routers trust that. Is that correct?
Yes and no. So the idea is, of course, that people may make mistakes. So basically, if you sign up with an ISP and you buy a book about BGP and you start typing, then you could make a mistake. It's possible. So what ISPs really should do, usually do, is that they have filters that only accept from their customers what their customers are supposed to send. So only the prefix that they know belongs to their customer. Now, so for simple customers that only have one or a few prefixes, that's fine, it works. There are, of course, some ISPs that don't do this, and then bad stuff happens sometimes. But the trouble is, if ISPs connect to each other, and they all have hundreds of customers with all a few prefixes, so that's 1,000 prefixes for one ISP. So that would be a very long filter, but also a filter that changes every week. So that's not doable to manually filter that. So basically, the big issue is between the ISPs. And yeah, if you don't have any mechanism to make sure only the correct stuff gets in, then yeah, I don't know if that means you trust them, but you don't really have another option if you don't have the mechanisms. Now, fortunately, we do have a relatively new mechanism, our PKI, that helps, but it's not foolproof.
I am aware from some security news sites that sometimes a ISP either maliciously or by accident advertises routes that it does not own. How can that happen?
There are a bunch of ways. There's actually an RFC from the IETF that lists 6 of them, and you can even think of a few others. Do you want some detailed examples?
Yeah, sure. That would be great.
Okay, so basically the most famous one is the whole YouTube Pakistan incident in 2008. What happened there is that the Pakistani government didn't like some videos on YouTube, so they told the ISPs in the country, I want you to block YouTube. So one ISP did that by creating a route in the routing table that points to a null interface. So all the packets that match that route basically go away. So that's a really good way to get rid of packets you don't like without having to set up all kinds of firewalling rules. But then what they also had was a mechanism where all the locally known routes were injected in BGP. So without specifically telling the router to put that null route in BGP, that happened. And then it went out to the ISP who didn't filter their customer routes. So they got the prefix from the YouTube servers from this Pakistani ISP, and they sent it out to the rest of the world. And to make things even worse, it was a longer prefix. So the longest match first rule kicked in. So that completely overrode other considerations, such as the length of the path. So even though the path was long, it would still draw all the traffic for the YouTube streaming servers to that Pakistani ISP where it disappeared. So YouTube became unreachable.
How long did it take for people to figure out what happened and fix it?
Oh, well, it was a long time ago. I think people started realizing what was going on pretty quickly within maybe 10, 15 minutes. And then there are these forums where network operators talk to each other, such as, for instance, NANOG, North American Network Operator Group. So they warn each other, this is going on. And then I think people started filtering out this incorrect information in BGP. And I don't know how long it took for the problem to actually be solved, to go away. If I had to say something, I think some number of hours.
That sounds like it was a mistake, but are there security attacks involving BGP where you're intentionally trying to route traffic somewhere that it doesn't really belong?
Yeah, the thing is, it's hard to tell. For instance, there was one time in 2010 where for, I think, 15 minutes or something, huge part of the internet was all routed to China Telecom. And yeah, people were asking, is this an attack or are they trying something to see if it works? Or was it just a stupid mistake? But there are things that were obviously attacks. So, for instance, one thing I've heard about, but I don't think I've seen any actual detailed write-ups, is where spammers take unused IP address space, announce it in BGP, start spamming because these addresses are unknown to the anti-spam software. And then they go away and nobody can see where it came from. I'm not sure to what degree it actually happens, but there was one incident. I don't know too many of the details where someone injected IP addresses of a DNS server into BGP to send out fake DNS replies, to reroute a domain name, to intercept cryptocurrency.
Last thing I'd like to ask, since this is software engineering radio, I could say as software engineer, I don't get exposed much to BGP, but is there a use case where I am running some application in a particular data center and I'm going to move it physically somewhere else? I might reach for DNS and say I'll get a new IP address in my new data center and I'll change the DNS record to serve the new IP address. But are there cases where I want to take the IP address with me when I move something?
Yeah, there's a bunch of applications where they hard-code IP addresses, sometimes as a way to limit the number of licenses that can be used or something. So that's always very annoying. But I think the main thing where you would want to do that for a good reason is if you want to have very high availability or very high performance services on the internet. Then, of course, if you put that somewhere, then the other side of the earth, it takes a long time for the packets to get there. And if it goes down, then you're gone. So then you would like to use Anycast. That means you have the servers with the same IP address in different places. This is especially something that happens a lot with DNS. And then the BGP will route the packets to the closest one. So you have the best performance. But then the thing is, if the service stops working, then you need to withdraw that prefix from that location. So the rerouting can happen to other locations. So there you have to have a tight integration between monitoring the service and influencing BGP.
Great. Okay, that makes sense. So if I could see that for DNS, where a lot of services do have DNS hard-coded with IPs, so it would break a lot of things if you issued a new IP address for your DNS server. You really are stuck with it.
Right.
Okay. I mentioned your book that you've already published and that's available everywhere. Your new ebook, when will that be available?
Well, the thing is, life keeps getting in the way, and writing is it's like programming. It always takes longer than you think. So hopefully, maybe 6 weeks or something, I'll be finished, and it will be up on Amazon and Apple ebook stores. And of course, if you look me up on Twitter, I'll send out a Twitter message to tell everyone about it. I'm very easy to find because you just have to type my first name, and then you find all the links to everything I do.
Do you have any other presence on the internet you'd like people to check out?
Yeah, when I wrote the book for O'Reilly, I created a website that, with some modesty, I called BGP Expert, bgpexpert.com. But I basically moved that stuff to iljitsch, my first name.com, where I have a section for IPv6, for BGP, and for some personal stuff. So that's a good way to keep track of what I write and what I do.
Iljitsch, thank you very much for speaking to Software Engineering Radio.
Thank you for having me.
For Software Engineering Radio, this has been Robert Blumen. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.